Good evening. You may remember that a month ago I showed you a picture of Halley's Comet taken with the 1.5-meter Danish telescope at La Silla in Chile. Now, here's the final version of that picture. Obviously, it's a false color picture, and remember, the comet is now way out beyond the orbit of Saturn, but there's still a cloud around the nucleus, and it doesn't seem to have changed much over the last few months. Also at La Silla, the NTT, or New Technology Telescope, has been brought into operation, and we have the first results. One of the most spectacular objects in the southern sky is the globular cluster Omega Centauri. Unfortunately, you can't see it from here. It's a huge symmetrical system of more than 1 million stars. Now, here's a picture of the center of that cluster taken by the 3.6-meter telescope at La Silla, and will you have a look at that rather hazy patch right in the middle? Now, here's the same area photographed by the NTT. And you can see that that hazy patch is now resolved into 3 stars. And the resolution there is 1/3 of a second of arc, which is quite amazing. So clearly the NTT is every bit as good as its makers had hoped. Another bit of news is that the Magellan Probe is on its way to the planet Venus. It was launched from the space shuttle Atlantis, and all seems to be going well. It will reach the neighborhood of Venus in August 1990, and we'll have a great deal more to say about it nearer the time. You know, from ground level, astronomers are rather handicapped. For one thing, visible light makes up only a very small part of the total range of wavelengths, which we call the electromagnetic spectrum. To the long wave end, we have first infrared, then microwaves, and then radio waves. To the short wave end, we have ultraviolet, then X-rays, and finally gamma rays. And for those reasons, one of the most important is that of the ultraviolet. And we've learned a great deal about it from one particular artificial satellite, the IUE, or International Ultraviolet Explorer, which was launched as long ago as January 1978 and is still working very well. Professor Robert Wilson of University College London probably knows more about it than anybody else, and we are delighted that he's with us now. Bob, welcome to the Sky at Night. First of all, why is ultraviolet astronomy so important?
Well, all regions of the spectrum are important. We found that out since the war, when the development of new technologies opened up, first of all, the radio spectrum, and then the advent of space research opened up all the other regions of the electromagnetic spectrum, with the result that there were new discoveries, startling discoveries, which put astronomy into a new golden age. But for ultraviolet astronomy, I would add the point that the atomic structure of the most common elements in the universe is such that the most sensitive spectral transitions due to them occur in the ultraviolet. It is therefore a richer region of the spectrum.
But of course you can't really study it from ground level because the ultraviolet radiation from space are blocked out by the Earth's atmosphere.
That's correct. Even from the highest point on the Earth, say Everest, there's no way you'd be able to observe the ultraviolet radiation at that point. So you have to go above the atmosphere. The orbit we've selected for IUE is a very high orbit, actually, selected because its period is 24 hours, so we can maintain continuous contact with the spacecraft. It's elliptical, varies between 26,000 kilometers and 46,000 kilometers in height.
And you have special ground stations?
Yes, we have 2 ground stations, one in the Goddard Space Flight Center in the United States, and one in the European Space Control Station, which is just outside of Madrid in Spain.
Now, what are the special features of the IUE?
Well, the model shows it's an observatory, has a telescope, which is housed in this tube that feeds 1 or 2 spectrometers. It has to have all the mechanisms that can allow it to operate. In space, it has to have an attitude control system, enabling the spacecraft to be turned and pointed to any object and then control for observation on that object, mechanisms. It has to be able to send its information to the ground station via antennae here, and of course it needs power in order to do that, and the power is generated by these solar panels here, which turn sunlight into electrical energy. One disadvantage of the operation in total sunlight is that we need a baffle system that's very effective, because the solar radiation flux is 16 orders of magnitude greater than that of the objects we want to observe. So that's a major requirement to reduce it to that extent. And we have a baffle system which is angled so that if you are observing a star, the sun will be in some position on the screen that's shown there, and the sun the system can't go too near the sun. The sunlight must not enter directly into the inner tube. Only diffracted light is allowed to enter there. Then the diffracted light can only get further by multiple scattering every time it strikes the wall. There's another baffle beyond that point which kills direct reflection, so it can only go in by multiple scattering. Then we have two internal hoods, which people always think means you can't get any light through at all. These, in fact, are such that only scattered light in the direction of the starlight can ultimately reach the detector. That system has worked perfectly. We've never detected any scattered light. You see here a cutaway which shows again the baffling system on the walls, the two internal hoods, and to the left of that screen is the spectrometer compartment with the two spectrometers in there.
But if sunlight were going to be a real problem, as it clearly is, then why did you select that particular orbit?
For operational purposes. It means that the system is continually in contact with one of the two ground stations we mentioned, and they have total control. So what you have is a spacecraft in orbit and a ground station, which also has an operator, has an observer, an astronomer, and that is the system which is of tremendous power. Let me take you, or take the viewer, through an operation sequence. Supposing the viewer has made a proposal, been fortunate enough to be allocated time on the IUE, then he or she has to go to the ground station. Goes to the ground station with an observing list and starts with the first target. Tells the system that this target is in that position, gives the celestial coordinates. So the whole spacecraft will be slewed and yawed until it points to that object. At that point, the field of view, whatever the telescope is looking at, is transmitted down and displayed on a screen in front of the observer, and you'll see here an actual photograph of such an image as it came up. A very simple one, Jupiter and 3 of the Galilean satellites, and it won't take much astronomical knowledge to identify which of those are the case, but people observe lots of other things in Jupiter, and for example, showing a rather complex situation, a star field, as shown here, will mean that the observer from a star chart obtained on the ground will have to say, yes, I know it, I recognize the pattern. This is the target object, and instruct the computer who will put the thing into the slot of the spectrometer. But in addition to that, the gyros are told where their position is, so they update exactly their position ready for the next slew. Having done that, the instructed system is told to observe for whatever it is, 1, 2, 3 hours or more. And at the end of that, the actual spectral image is relayed also onto a screen in front of the observer, who looks at the image to decide whether it is of sufficiently high quality that it is, will pass on to another object. This shows you an Ashell spectrogram, which is the kind which comes out of the IUE.
You know, over the whole 32 years of the sky at night, we've never once mentioned the Ashell Principle. Will you say something about it?
Yes, it is a single spectrum, although you see it in bands like that. It has in fact been cut up into narrow strips, cut up optically into narrow strips by a very elegant method, and stacked in a two-dimensional format on the face of a modern detector, a detector which was actually developed in the UK. And so each strip is one part of the total spectrum, so if you explode them out and then move them along, as this animation shows, until the end, you put them side by side by side, and then that is one single spectrum in the form that the astronomer and astrophysicist is used to have.
A very neat method indeed. Well, the IUE was launched way back in 1978, so it's now been in orbit for more than 10 years. It's even beaten Mrs. Thatcher to it. Did you expect it to last for so long?
I think even the most optimistic of us didn't expect it to be quite that long, but we did know that it was important to have a long lifetime, because long exposures and time is important in astronomy. And so we set what was then regarded as an over-optimistic aim of 3 years. We said 3 years for the lifetime of IUE, and people thought we were being far too optimistic. In the event, we are now into the 12th year, but we did things to try and guard against early failure. For example, we ran a special high-priority program covering every object in the sky from the solar system out to quasars and everything, just in case it failed early. At least we have this high priority data bank for people to work on.
I believe one of the early computers did fail straight away, didn't it?
No, it gave some difficulties. It turned out to be schizophrenic in that its only function is to control on the object after it's been found by the observers and nothing else. But in an early stage, we suddenly found that the spacecraft was slewing directly towards the sun. Fortunately, the attitude control engineer was present, said, give me the housekeeping data. He found out it was a computer telling it to slew towards the sun. So he said, tell the computer to do nothing more, cut it out the link, and put it in a safe position. It was found later it was a temperature effect. It went schizophrenic when it ever went above.
Now, can we start having a look at some of the results, beginning, I think, near at home with the solar system? Now, you can't look at the sun because it's too bright. You can't look at the planet Mercury because it's too close to the sun. And you can't look at Pluto because it's too faint. But that leaves plenty of scope.
Yes, in fact, almost every other primary body in the solar system that you haven't mentioned has been studied by IUE. One which always gives me great interest is the Io Taurus.
Io being the nearest big satellite of Jupiter.
That's right, and it was Voyager who discovered there was a plasma torus around Jupiter which was centered on the orbit of Io. Now, IUE has observed this torus now for 10 years almost, has established a temperature, it's 50,000 degrees, it's quite stable, remarkably so, and we now know that the injection mechanism that produces the torus is the volcanic activity on Io.
Yes, Io, of course, is the most extraordinary satellite with sulfur volcanoes going up all the time. That's a natural Voyager picture. You can see a volcano erupting there.
That's right. When the material goes out with sulfur dioxide, of course, it's neutral, and it will not notice the magnetic field of Jupiter, which is passing across the planet at very high velocity until it's ionized by any kind of collision, at which point the magnetic field just sweeps up the ions and takes it around in the whole torus, and it's like a vapor trail, but in reverse, in that the vapor trail is ahead of the satellite because the magnetic field is traveling far more quickly than the velocity of Io itself.
Now, let's go further out, and I know you're very interested in stellar winds, which obviously are not winds at all, but streams of electrified particles coming out from stars, and our sun has quite a pronounced wind. But there are many stars which have stellar winds far stronger than the sun's. Some of these stars are very hot, luminous, and unstable. One of them is called P Cygni, and you can see that now. It's just about visible with the naked eye. Binoculars show it clearly. It's in the cross of Cygnus. There's Deneb and the lovely double star Albario. And P Cygni is not very far from the center star of the cross. It's variable, magnitude 5 now. Way back in the year 1600, it actually flared up to magnitude 3, and for a time it was classed as a nova. But of course it's not. It's a peculiar, very luminous variable star, and it has a very powerful stellar wind, and there are plenty of others like it. Bob, what has the IUE told us about stellar winds in general?
Well, it's told us that just about every star has a stellar wind. We knew our sun had one. It's a very light wind, but energetic. But we now know that as the sun evolves towards becoming the red giant, that wind will become heavier and heavier, but less energetic, until by the time the red giant will be quite a heavy wind. But the real stars with the real heavy winds are the very luminous stars, where the radiation pressure is so great that it actually blows the matter off. And some of these are so heavy that it's impossible to explain the mechanism for producing the winds. The radiation pressure plays a part, but the Wolf-Rayet stars lose a solar mass in typically 100,000 years, and we don't understand that yet. But they are dynamic objects. They are not gravitationally contained at all.
Well, that mass loss is certainly very great. Well, what about binary stars, star pairs?
Lots of stars, of course, are in pairs, and the ones which have been studied, particularly by IUE, are those in which one of the pair is a compact object. If you have a binary system in which one object is a neutron star, and there are several of these, then what happens is that the normal star sheds by tidal effects and everything material, which then streams down, spirals into the neutron star. It gets hotter and hotter and releases a lot of energy. In the case of a neutron star, by the way, the sun would fit into central London if it was a neutron star. The escape velocity at the surface is 30% the velocity of light, which means if something falls in it, we've got the 30% the velocity of light. And that means that the energy release is far greater even than a fusion reaction, where you only get 1% of the Einstein mass energy. And we believe that energy source is also the one which powers the quasars.
Now, what has IUE told us next about galaxies such as our own?
Well, in the case of our own, it came up with the fascinating discovery that our galaxy is bathed in a very hot halo and a very extensive halo.
What's it made of?
It's made of the normal components that you'd see in the interstellar medium, normal cosmic distributions. Its temperature is something like 200,000 degrees. This means that its pressure is sufficient to maintain itself extensively against the galactic gravitational field. Indeed, it's almost as extensive as the radius of the spiral arms themselves, as this is shown here. At the same time, it explained immediately one set of absorption lines which had puzzled astronomers for many years, which were observed in the very distant quasars, where in between there were these absorption systems of the carbon-4 and everything which you see in our own hill. And these are simply the halos of the intervening spiral galaxies through which the quasar light is passing.
Well, quasars are certainly a problem, now believed, I think, to be the nuclei of very active galaxies themselves. But what has IUE actually told us about the quasars? And I'm thinking particularly, of course, of the gravitational lens system and the apparent doubling of a single quasar.
Well, quite a lot about the quasars themselves and their nature, but the one I'd like to discuss is the double quasar that you've referred to. This is a pair of quasars very close in the sky that seem to be identical. Here is a direct image of them taken in the optical region from beautiful observing sky in Hawaii, and you will notice that one of them is slightly elongated on the right. Now, if we assume they are identical, we can take the right-hand image away from the left-hand image and see if there's anything left, and indeed there is something left, and that is an intervening giant elliptical galaxy. And the reason for the doubling is not that there are two quasars, but there's one quasar, and that intervening galaxy is acting as a gravitational lens and given the impression of two quasars when indeed there are only one of them in the sky. It's shown on this diagram where one light ray goes above the intervening galaxy, one below, and is observed and assumed that you have an image at A and an image at B.
Now, what's the real importance of that?
Well, one very important development is that studies with IUE have managed to detect a time delay, because the time delay between the two paths is finite. One path is shorter than the other. The light from A will reach the observer before the light from B, and if you can measure that difference, you have a direct measurement of the distance of the quasar, a direct measurement of the expansion of the universe. IUE detected A to diminish in intensity by about a factor of 2, and then observed the same event in B 21 months later. So that tells us the distance of the quasar. We know its velocity, so we know for the first time the universe actually is expanding out to those very distant levels.
And how far away is the quasar?
About 10,000 million light years, or the universe then was about 27% of its present age.
Well, the IUE clearly has done a tremendous amount of useful work, but it's still operating. It won't last forever. How long has it got to go?
Well, the ultimate thing which will need to stop IUE is when it runs out of power, because the solar panels are decaying in efficiency with time because they are bombarded by the energetic particles out there in space. But at the present reckoning, they think perhaps another 3-4 years even.
And what next?
Well, the next ultraviolet satellite, of course, the next satellite in ultraviolet capability is the Space Telescope, which we've all been waiting for so many years, and now scheduled for launch, I believe, in mid-1990. That has an ultraviolet capability, which I believe will be the most important aspect of the Space Telescope.
Well, quite clearly, ultraviolet astronomy has now become an integral part of modern astronomical science. It's new, and it's very rich indeed. Bob, thank you very much. And I think we've got to realize that the IUE, the International Ultraviolet Explorer, is just about the most successful artificial satellite ever launched. From both of us, good night.
There's a second chance to see that programme next Saturday afternoon on BBC Two at 3:25, and the next examination of the sky at night will be on Sunday evening, the 4th of June.